Hello everyone, my name is Zhen Yu. I'm a PhD student from University of Toulouse. I will present improving the performance of WCET analysis in the presence of variable latencies in this video. Critical real-time systems often require to ensure temporal properties of tasks. For example, an aircraft fly-by-wire system must execute any command of pilot within a certain time in any condition. To achieve that, one is to compute the worst-case execution time, so-called WCET, of tasks by static analysis. The analysis must consider the hardware of the system and provide a safe upper bound of execution time in number of processor cycles. As we need the execution time in processor cycles, we have to work on assembly code. So we represent the program by a control flow graph. The program is split into several blocks called basic blocks. These blocks contain only jump or destination of jump and the beginning or the end of block. So the execution within each block is totally sequential. The edges represent the possible order of execution between basic blocks. As an example here, a function computing the maximum element of an array, we can find all its control flow in the control flow graph, except this if, which is optimized by a conditional assembly instruction. Now, since the execution of each block is sequential, we can compute the worst-case execution time of each basic block. Let's take PP4 as an example. Since the processor is pipeline, we also want to consider the overlap of execution between blocks. So we want to take a predecessor of PP4, which may be PP4 itself or PP3. Let's take PP3 as an example. So now we are modeling the execution of PP3, PP4 on a simple in-order execution processor. The processor has a pipeline of 5 stages: instruction fetch, decode, execution, memory access, and write back. The assembly code is at the left, and the execution graph is at the right. The execution graph represents the execution of instructions in the pipeline of processor, where each node represents the execution of an instruction in the pipeline stage, and each edge represents the dependency between nodes. There are two types of edges. The solid edge indicates that one node can only start after the end of its predecessor. For example, the stage decode of instruction 0 can only start after the end of stage fetch of instruction 0. This type of edge translates the pipeline order, these horizontal edges, and the program orders, these vertical edges, and data dependency from the stage memory access of instruction 2 of stage execution of instruction 3, for example. The dotted edges indicates that one node cannot start before the start of its predecessor. For example, the stage fetch of instruction 1 cannot start before the start of stage decode of instruction 0, which free the queue between fetch stage and decode stage that allow instruction 1 to enter the fetch stage of pipeline. This type of edge represents the concurrent use of resource, in this case the queue of size 1 between fetch and decode stage. With all these dependencies, we can compute the start time of each node by the latest start or release time of its predecessor depending on the nature of edge, represented by delta, and the latency of its predecessor node or edge, represented by lambda. Now back to the example. Supposing that each node takes 1 cycle to be executed, so the stage fetch of instruction 0 will finish the execution at cycle 1, decode cycle 2, 3, 4, 5. 6. We also take the latest time of predecessor. For example, the stage executes of instruction 3 takes maximum between 5 and 6, which is 6, and plus its own latency, we have 7 here. By doing so, we will find the total execution time of BP3, BP4 will be 13. Now, to obtain the execution time of BP4, we do simply 13 minus 6, which is the execution time of BP3, and we have 7, the execution time of BP4. However, the execution time of each stage is not always one cycle or a constant cycles. There may be some hardware effects, for example branch predictions, cache access, that may have different latencies according to the execution context. So we defined what we called events to represent the occurrence of variation of execution time. And we denote P gamma the set of all possible combinations of activation or non-activation of events, and the small gamma a particular configuration of big gamma. Back to the example, we can consider 5 events: IC0, IC, and IC1, the access of instruction cache, and DC2, DC3, the access of data cache. The cache analysis confirms that IC always results a cache hit, hence not considered as an event. So now, what happens if we want to include events into the computation of execution graph? If we represent symbolically the execution time of each node, we can find 1 plus 9 times E0 at the end of stage fetch of instruction 0, which means D cycles if E0 is active, one cycle otherwise. Now, doing the same computation like before, but with variable E0 to E3, we can find the execution time of the block here. There are two remarkable things. One is that E0 disappears when we subtract the execution time of PP3 from the execution time of PP3, PP4. The second thing is that if E2 is active, the maximum between 9 times A1 and 10 will always be 10, which means E1 has no effect if E2 is active. So if we enumerate all possible execution times according to the activation of events, we have the table here. With 4 initial events, we have E0 disappears, we have only 5 execution times, which is much less than 2 power of 4, 16. In fact, the pipeline of processor is designed to absorb latencies during execution. This absorption creates similar execution pattern in different configurations. For example, the case where E1 is shadowed by E2 here. So now we want to find an efficient way to represent this relationship between configuration and execution time by utilizing this property of pipeline. First, we represent this table as a decision tree. Events on nodes, execution times on the leaves. The solid arrow indicates that the case where the event is active, and the dotted arrow otherwise. There is a common technique used in binary decision diagram, consists of sharing identical subtrees and leaves to reduce its size. If we apply the same technique here, we obtain what we named XDD, stands for execution decision diagram. Comparing to the full tree, we have the E1 disappear here and here. The leaf 16 is shared by several nodes. XDD is defined as an inductive structure, a leaf with an execution time K, or a node with an event E. The subtree where E is inactive, F overlined, and the subtree where E is active, F. The depth of events depends on the total order that we define on E, which ensure that greater events are always deeper. For a given such order on the domain of events, E, XDD is canonical, which means that there is a unique XDD to represent the relationship between configuration and execution time. To ensure the physical unicity of subtrees and leaves, we have implemented a memory unit, a memoization unit to keep XDD minimal. Now, we want to use XDD in execution graph computation and compute all possible execution times instead of one execution time and time. The max and addition on natural numbers are imported on the domain of XDD. The algorithm of computation is kept as before. In fact, the max and the plus in XDD forms a max plus algebra on XDD domain that represents and computes all combinations of execution time simultaneously. Now we define these operators. In fact, we can import any binary operation on natural number on XDD. Here is the algorithm. In case A, if two XDD are leaves, we apply the operator on natural number directly. In the case E, F, and G, if they are nodes, we descending in both trees according to the order on events to keep the order of events in the new tree. If the node which is being created has identical subtrees, which means it should not exist, we will ignore it. That is the case B, C, and D. Since the algorithm apply recursively on subtrees of XDD, and considering the possible similar subtrees during the computation execution graph, we have implemented a memoization unit for each operator. It records the result between XDD subtrees for the first time and allows to reuse it if the identical computation is needed later again. Another particular optimization is applied to the max operation between XDD. If all leaves of one XDD or XDD subtree is greater than another one, we can stop the computation and take the greater one. To avoid recursive check at each step, we plant a pair minimum leaf and maximum leaf at each node. However, the performance of XDD stands majorly on its size. In another word, if the execution in the pipeline allows XDD to reduce its size or not. So, we have experimented XDD using Ottawa Toolbox on Darkly benchmark set to see if the reduction is empirically effective. These figures show the number of nodes and leaves of XDD in logarithm scale with respect to the number of events on a simple in-order execution processor. Each blue point represents the analysis on one basic block, and the red line represents the case where we have no simplification at all, so 2 power of the number of events. It's clear that XDD reduces impressively its size. It has only 10,000 nodes and thousands of leaves when the number of events reach 100. On a more complex in-order but superscalar processor, it shows the same trend but with slightly worse and more variable performances. Finally, we compare XDD to the existing analysis that Ottawa uses, called eTime, which is an exhaustive algorithm. The x-axis are benchmarks ordered by the analysis time of eTime, and the y-axis is the analysis time in logarithm scales. We had to cut each block into smaller blocks containing maximum 15 events because e-time would not be able to finish in a reasonable time beyond 15 events. Even in such conditions, XCT shows impressively better performances than e-time on most of benchmarks. E-time is only slightly better in the smallest benchmarks and takes very little time compared to others. To conclude, we have presented the structure XDD that improves the performance of pipeline analysis with execution graph. The performance of XDD relies strongly on the absorption effect of pipeline that we try to validate statistically by experiments on two different hardware architectures. As future work, we will try to experiment on more and different architectures. Considering the performances of XDD, we have also intention to extend XDD to represent more precise execution context of basic blocks in the control flow graph of whole program. We also have the plan to extend XDD for out-of-order pipeline analysis. We expect that the absorption effect is stronger in the out-of-order pipeline, which may improve the performance of XDD. Thanks for watching.